So I'm Ben Clifford, and I'm going to be talking about a Python library called Parsl, which is for productive parallel programming in Python. And monitoring Slack is my colleague Yadu. So if you ask questions in that same 00 workflows Slack channel, you might get answers from him rather than me. So this is a hands-on demo. You can follow along if you want to. The install instructions are in the same GitHub repo in 00 workflow/Parsl demo. So right next door to Tom's demo. And we're going to do this inside the ALCF Jupyter system. So if you follow these instructions, it will lead you to logging into jupyter.alcf.nl.gov in your web browser. And it will talk you through installing Parsl into that. And if you do that, you will end up with something that looks like this. And you choose the Parsl tutorial notebook, and you will end up with something like this. So let me just clear this and restart it. Okay, maybe I can make this text a bit bigger. Oh, maybe not. Okay, so Parsl is a Python library for building workflows to put together pieces of code. So in examples, for example, production applications that I work on, we've got a lot of astronomy tools. And they run for a minute to an hour, for example, and we want to put all of these pieces together in a particular way. And Parsl is the library that lets us do that. So I'm just going to work through some simple examples about how this works and hands-on. So I'm just going to install import Parsl into my environment, and when I run that, hopefully, if it works, we can see we've printed out Parsl version, and it's version 1.2.0. So the first thing in this Python environment is I'm going to initialize Parsl, and I'm going to do it by running this parsl.loads command, and it's going to use a configuration that I've just imported and defined elsewhere. When we come to the end of the talk, I'll talk about configuration a little bit more. But for now, just believe me that this is an okay configuration. And so now we can run some stuff. So if you look here, there's a little Python function called hello, and it just returns the string hello world. And I'm going to say I want to use this as a building block inside a Parsl workflow. So to do that, I put this annotation on the front. Well, it's called a decorator in Python, @Python app. And then now to invoke it, I say hello and then ask it for its result. So the syntax is a little bit more verbose than regular Python, and you'll see why in a bit why we need to do that. So if I run this, it should not be too unexpected. It just says hello world. And you can pass in parameters. Excuse me, just 1 second. You can pass in parameters. So here's a fairly obvious multiply function. We pass in 2 parameters and we multiply them together. And the same, I'm going to multiply 5 and 9 and get the result out. So 45. Nothing unusual there. One thing that's a bit interesting is Parsl can help you run these apps, these little chunks of work on other computers. And so if it does that, it doesn't import the whole environment. So if you want to use another library, such as the time library here, you have to import it inside your app definition. You can't do it at the top level. So this one, we're going to import time, we're going to sleep for a bit, and we're going to output hello world. So a lot of the demonstrations that I do with Parsl, I do pretend computation by putting in these sleeps, and you could imagine that there's some actual useful computation happening there. So when I run that, it will sleep for 5 seconds and hopefully give hello world. So that is, if you're implementing some code in Python, you can use this Python app decorator. You can also just use Unix command lines, so bash command lines, by using the bash app decorator. So here's something simple. We're going to run echo hello world. We're going to direct the standard out to this file and the standard error to this file. Okay. And if I run that, we're not going to get a result back because it's a Unix command. It doesn't return a result. It just outputs to files. But then straight away, I'm going to read in what's in the echo hello standard out file. And it's added. You actually get it multiple times here because every time I run it in testing, it adds one more hello world onto the end of the standard out file. So I'm going to skip this next section for now, and I might come back to it. Okay, so I said we have this awkward syntax where I have to say hello or whatever, and then put dot result on the end. Okay, you don't have to put the dot result straight away, and that's why we have it structured this way. When you run an app, when you invoke an app like this, what you get back is what's called a future object, and that happens straight away. So even if this app is going to take 2 hours to run, you're going to get this future object back immediately. And then you can say, well, down here we ask for its result, but we can also say, is this future done yet? You can ask a few other things about futures. So if I run this, you'll see first it says, no, it's not done, this line. Then now here it waits for the result, tells me the result, hello world. And at that point, if I make that same question, is this done? I'll get told true. Okay, so what we're doing here, and there'll be some more complex examples later, is separating out the submission. You can imagine this is a little bit like a job submission or a task submission, and then waiting for that task to complete. And in some of the earlier talks where you did a qsub command to submit a task, and then you could look at qstat to see if a task is completed. That's kind of what a future is, giving you an interface here to submit and here to check if it's done. Let me skip the data section as well. Okay, so we don't have to just submit a task and then wait for it to give an answer. So here I've got 2 different apps defined. One which picks a random number, so it's called generate, and it just uses the standard Python random library to return a random number. And then I have another app. This one happens to be a bash app, which is going to write the parameter you pass it into a file that you ask it to write to. Okay, so here, let me just comment out this line. Here, we're going to make a future, which is the future that's going to contain the result from a generating a random number between 1 and 10. And here we're going to make a future that is going to represent invoking the save app to save the random number into a file that we're going to call sequential output.txt. And I'm just going to add an extra line in here that says here waiting. Okay, so if I run this, what will happen is straight away we'll get to here waiting, I hope. Oops, missing an import. It's my fault. I'll do that. Yeah, okay. So what happened here was we invoked generate and we got a future. We straight away invoked save and got another future, but I noticed I didn't ask what the result of this future was. I just passed the future in straight away. And Parsl knows, because these are both Parsl apps, it knows that it can't run save until generate has finished. Okay, so although this looks like it's sequential in Python code, it's actually sequential inside Parsl. And we'll make some more complicated data structures later on. Here we go. So we could run this in parallel. What we're going to do here is we've got similar generate command. This one's got a sleep in it now. And I'm just going to launch 5 copies. So when I run that for loop, it's going to call generate, it's going to get a future, and it's going to give me a list. It's going to populate this list of random numbers with 5 futures, one representing each invocation of generate. And then when that's done, when those apps have all been submitted, but not when they're completed, I'm then going to make a new list called outputs. And for each of those futures, I'm going to wait for the result to appear. So what can happen here is, say I submitted 10,000 generation commands. It would give Parsl the opportunity to run all of those at once. So instead of this for loop being a sequential execution of generate, it's a sequential submission of a large number of generates. And Parsl can run them with whatever it has available, however many CPU cores you have available to run. And the results. There we are. So well, they don't look terribly random, but theoretically random numbers. Okay, I'll skip these two and come back to them later. And so the final interesting example here is this Monte Carlo workflow. So we're going to do a little bit more complicated workflow. We're going to estimate the area of pi by running a little Monte Carlo simulation 3 times. And that simulation is called pi. So it's defined here. And each of those is going to return an estimation of pi. And when each of them is completed, we're going to pass them into this mean function here, which is going to compute the mean. Just add the 3 numbers and divide by 3. And that will give us an estimation of pi. Okay. And so the definition is that we're going to call pi with num points, number of iterations. And so we're going to call it 3 times with 1,000,000 iterations. If I set that, let me comment out this line. If I set this going, we fairly rapidly get an estimate for pi. So you can see that here I made 3 invocations for pi. So that gave me 3 futures, A, B, and C. And then I passed those futures into mean here, A, B, and C. And I don't anywhere ask for the result. So I could have asked for the result of A, B, and C if I wanted to in this line. That's allowed, like this. But I don't have to. I can just ask for the end result of the whole workflow. This average value of pi that is coming out here. And Parsl will make sure that this result call doesn't return until this entire graph of tasks is run. So everything I've shown so far is running on just on a single host on the server that is running at Argonne, that is running this Jupyter notebook. But you can configure Parsl to do other kinds of execution. So at the very start, right up here, we did a Parsl.load with a config, and that config just was one of our standard configs that we supply. I just imported it. But down here,
Ben, we have a question in Slack.
Yep.
Maruti is asking if we could explain the differences between Parsl versus Ray.
Between?
Parsl versus Ray library.
Hold on. I don't really know about Ray, so I don't know if Yadu, if you have experience there.
Very barely. What I would say is that Parsl is like intended for running workflows on like computational facilities like ALCF, NERSC, and whatnot, where the goal is that you have a workflow that is, a DAG of tasks that you want to run at scale. Ray is generally intended for like the machine learning learning sort of like setups where you have tasks where you need like some stateful actors. So the model that Parsl uses, where you have tasks which are like completely like pure functions which like pass data in and data out, is not quite what you get with Ray. So there are a bunch of like computational differences between them. Like the computational model is quite different, but I could give you more differences if there are like specific use cases, and I can tell you how it might be different if you use Parsl versus Ray. I'm not sure if that completely answers the question, but it's pretty big there.
Mm-hmm. Yeah, so there's a specific computational model with Parsl where you have these apps and they take in a value or take in some values and they return a value, and that's it, they're done. There's nothing else going on there. So if you want to do more interesting state, that happens inside your main Parsl code, or your main Python code here. If you want to do that more interesting stuff, to plug those building blocks together, but the building blocks just take some inputs, do stuff to it, and produce some outputs. Okay, so configuration. We had that parsl.load command. Here's a different way of defining local execution, and in this one, we're saying we're going to use eight threads on the local machine instead of 2, which is the default. So let me say parsl.diff cleanup. Okay, parsl.load local threads. Okay, so what I'm going to do now is this will clear out the old Parsl configuration and reinitialize Parsl with this new configuration. Oops, except it won't. That's okay. So now I've initialized the new Parsl, and theoretically I can just go back here and run the same thing. Oops, I've put a typo in. Result. There we go. And the same code runs. Okay, so I've just swapped out the configuration and run exactly the same workflow code, and it's run. And that probably doesn't look particularly impressive at the moment because all I've done is changed the number of threads being used locally. But another configuration, for example, that starts getting interesting on large systems like at ALCF is we can have a much more complicated configuration using what's called the high throughput executor. And what that lets you do is launch pilot jobs onto nodes on Theta. And this configuration will launch just one job of one job with one node in it with 30 seconds of wall time. And it will run all of those commands in introduction for running qsub and ap run and things like that. Parsl will, if you give it this configuration, this tells it to use ap run. This tells it to use the Cobalt qsub commands. Up here, I've put in my theta allocation and my theta q that I'm going to use. So these are basically all of the parameters that, if you saw the intro session earlier, just in a more Python configuration syntax that's a bit more amenable to Parsl. So if I create that configuration, and then clean up Parsl and load it again. Fingers crossed this will work. Now, if I go to a terminal, I hope, oops, let's get a new terminal. I hope that I can say qstat ubenc, and you can see there that Parsl has started up a job running, which will take a while to start up.
Hey, Ben, while we wait, there is a question on Slack from Thomas. He says, yeah, right there.
Yeah, so
parallel copy.
Yeah, we copy a lot of data files over for our runs, and it's all done serially. We're doing multiple copies at a time, be a good use for Parsl. So Parsl, it looks like I'll have a bit of time to go back, loop back and show the bits that do this, but Parsl can do file staging, and it can do those file staging jobs as individual Parsl jobs. So it can parallelize those if that's what you want to happen, yeah. So let's have a look. Okay, it's running now. So these are the qstat commands, same as in the intro. And hopefully now, you're going to have to believe me for this bit. But if I run pi again, without any other modifications, this workflow, which is doing its science, I didn't change anything but the config, and it still computed a pi estimation for us, but it did it now inside the worker nodes, running on Theta instead of inside the Jupyter environment. So that's one of the things we're really pushing on, is you try and define your workflow and in a way that is independent of where you're running it. And then you define a configuration that describes the interesting stuff about where you're running it. So that hopefully, it's nice, it does work sometimes, not always. You can run stuff on your laptop, or you could run the same code on the Argonne supercomputers. And I've also successfully ported code this way between running at Argonne and running at NERSC, for example, without really needing to make big changes to the code other than this configuration. Okay. So let's go back and look at the files. So I skipped all the file sections, but back here, here we are. So the apps so far, we talked about parsing in just Python objects. And if those need to go over the network to get to worker nodes, Parsl will serialize them. But you can also create these file objects and pass those into applications. And you can either pass in a file system path, or you can pass in a URL. And then you can configure data providers that tell Parsl how to get a file from your submitting system into the place where it's needed for execution. And so there's a combination here of declaring what it is what the file is. You declare here as a parameter, and then in your configuration that is site specific, you can declare how you can move a file to and from that site. So it might be using Globus, or it might be using HTTP or FTP. There's a whole pluggable mechanism there. And you can also, in the same way that you can order tasks based on result completion, you can also, let me find if we have an example for that. Here you can order tasks based on when a file has been created as an output file. Yeah. So I've got a few minutes left. What I can do is show you some slides about some of the applications that we've been using Parsl for, or that people use Parsl for. Okay, so everything I've shown so far is these silly little toy applications that mostly they take up time by doing sleep. But there's a whole spectrum of different science projects that we've been using Parsl for. The big one that I'm personally involved in is this LSST simulation and weak lensing sky survey project. So this is taking data from well, first simulating data for a telescope that hasn't yet been built, and then processing the results from those simulations, and later processing results from the actual telescope. So this it's going to consist of 10 years of a telescope taking photos of the sky at very high resolution every 30 seconds for 10 years. And this data set, then you have science questions that you want to ask. And that consists of maybe pre-processing every single frame or every frame in a particular area, and then combining certain frames together because they happen to be the same part of the sky, even though they're several years apart, and then doing some more sciencey stuff that astrophysicists know about that I don't know about. So those tasks, instead of being these little time.sleep 5, they run from say 30 seconds to a few hours, and we have maybe 100,000 tasks, for example, that Parsl will orchestrate together to give a result at the end. So that's the big project that I'm personally involved in. Yadu, do you have a favorite project that you want to talk about?
I mean, LSST is my favorite project. I would.
Okay. Everybody loves LSST.
Well, probably because it's basically been the best example for like demonstrating like the scale and the fact that you can run the same workflow across 2 different facilities, right? So which leans very much into Parsl's strengths. Yeah.
Okay, then I will end with just the slide of buzzwords, which is so really what I've shown in that or what we've shown in that code is just the really basic way of plugging these tasks together. So I showed this first bullet point here that you can run exactly the same code in different places just by changing that configuration. We've got other stuff going on. For example, we've got support for retries and checkpointing. So Parsl can say this task failed, I'm going to run it again for you. Or it can say this task you already ran yesterday, so I'm not going to run it even once and just use the result from before. You can configure it to run on multiple sites. We don't do it a huge amount, but it is possible. So you can say your configuration could be, here's how to submit something to ALCF, here's how to submit something to NERSC, and your Parsl can run stuff on both of those sites at once. It can scale up and down. So in the demo, when I made that configuration, it straight away submitted exactly one batch job. But what you can say is, as your workflow runs, there might be periods where you need a lot more nodes, or you have a lot more to do, and then there might be a quiet period because you're doing something that just runs on one core for 6 hours. And Parsl can dynamically submit more blocks of workers and kill blocks of workers as they become unused. We've got a monitoring database, which is an SQL-based monitoring database. So that's pretty interesting to start asking questions like, how long did I ran this command 10,000 times, or this app 10,000 times. Can I get a histogram of what the run times were, and start asking questions about why does the histogram look like that? We've got the data management stuff that I briefly touched on, which uses Globus. We've done a lot of stuff working with containers. So there aren't specific Parsl library features with containers, but it really overlaps very strongly in practice with moving between different sites. The containers are one of the biggest helps there for making that work. It runs inside Jupyter, the notebook server, you've just seen that. And one of the things that science loves to pay lip service to is reproducibility and claiming you know where all your output data files came from. So you can use the monitoring database we have also helps you work towards making that kind of claim. Okay, that's the end of the Parsl session. If you're interested, you can go to our website, which is lost up here somewhere. There, parslproject.org. We've got lots of links. You can get to our GitHub. We've got lots of documentation up there. If you want support, you can open an issue. Yeah. Okay. Any final questions?